Hi everyone, my name is Deb Chatterjee. I am a Senior Director of Engineering within Intel. We are part of the Cloud Networking Group, which our parent group is the Network Edge Group led by Nick McKeown, and we are a subgroup underneath called the Cloud Networking Group. For last couple of years, we have been working on this new type of processor for infrastructure offload that within Intel we call Infrastructure Processing Unit or IPU. There are other companies with similar products that they call the DPU. So in general, to address devices similar to IPU, DPU, etc., in some literature, this term xPU is used, and this presentation uses that terminology. To efficiently build software for these type of infrastructure offload processors, we have also created a development kit that we call Infrastructure Programmer Development Kit or IPDK. This is an open source initiative, and today in this presentation we are going to talk about how we can use the xPU and IPDK to do local storage emulation or storage virtualization. Typically this is done in processors, but the advantage of running it in the IPU is you can then free up the expensive cycles of the processor to do more interesting, more complex things on the CPU itself. And the infrastructure part gets offloaded. And I'll talk about more benefits of that. So roughly this is the agenda that I'll talk about this work of storage virtualization or emulation of local storage. I'll provide a brief introduction to this xPU as well as a brief introduction to IPDK. I'll show how a storage virtualization use case can be easily prototyped on a IPDK software target. This infrastructure programmer development kit can be targeted for multiple hardware devices as well as just pure software. So I'll show how this prototyping can start on pure software and how we can then move those to an actual IPDK hardware target. So what we mean by local storage emulation is essentially providing a virtualization of a remote storage, providing a layer of abstraction so that from the perspective of access, it almost seems like a local storage. The advantages of that is many. First of all, it provides an abstraction over the storage so that you can mix and match different types of storage devices. It provides disaggregation between the compute resources and the storage resources that results in an easier ability to replace, upgrade, remove storage or add storage as and when required. There are standard and mature APIs available to do these, so it also brings a level of programmability in the ecosystem. This happens being completely transparent to the client-side software and drivers. If there are changes in this side of the IPU software, there is no equivalent impact on the client side. And while this can mostly be done on a software platform, use of dedicated hardware can bring performance improvement, acceleration, and it also brings in a layer of improved security. So these are some of the benefits of both the local storage emulation as well as doing local storage emulation on an IPU as opposed to the CPU. Let's talk a little bit about the emergence of these xPU type of devices. I mean, what prompted Intel and other companies to come up with a new breed of processor to address this particular problem? I think when we talk about this, three trends are particularly important to recognize. The first trend is that the data center applications are bringing in need of hardware acceleration, hardware offload that is not often addressed by general purpose processors. For instance, Amazon has a query application accelerator called Aqua, and it was purpose-built hardware for accelerating key value type of storage access. And there are many applications, there are many examples like that which are not easily met within the traditional, CPU and its working model. So that's one trend. The other trend is the cloud service providers, their business model monetizing the CPU cores. This has resulted in another need to move the network infrastructure away from those cores, because let's say a cloud service provider like Amazon buys a 64-core processor from Intel, their expectation would be to run AWS instances on all 64 of those. And then if I say, wait a minute, 5 or 10 or some number of those will be used in just running the network infrastructure, otherwise your AWS instances will not run, then they're losing the revenue from those cores. And if you assume something like $1,000 per year from one core, then from 10 cores, it's $10,000 over a lifetime of 5 years. That's $50,000, and the cost of an xPU hosted offload is such a small fraction of that. And the third trend, which I think also played a big role, is this bare metal hosting. And once you have a bare metal hosting contract, then you are not able to run literally anything. Everything on that platform, on the CPU side, has to be given to the tenant. So these three trends resulted in the design and evolution of this new kind of processor called the whose main purpose is in offload of the network infrastructure. Whether you call it the IPU or the DPU or address them under the general name of xPU, there are some key trends, key common elements across these. First of all, the expectation is that these will contain high-performance, software programmable, multi-core processors. These can be x86 cores, these can be ARM cores, but that availability of those multi-core processors is important. And it is not just for running the control plane, it is also the fact that there could be some new emerging algorithms or applications which has not been completely hardware accelerated. So without putting a load on the CPU, you can just run it in pure software. If it's a new protocol or new algorithm, you can run it on the xPU. It definitely needs to have flexible and programmable acceleration engines, such as accelerating NVMe protocol or RDMA protocol, or handling the packet processing, the match action pipeline of P4 to have an engine like that. It should have stream-based interfaces for high-performance data movement. it should have some kind of either out-of-band management capability so that it is managed separately from the CPU, or in future, there can even be a new type of system design where this xPU is really the center of the platform. It is the one that boots up first and then takes other compute elements, the GPUs, NPUs, even the CPUs out of reset. This can be something like a platform of the future. And it definitely needs to provide a level of security isolation from the CPU so that anything running on it cannot adversely affect the CPU processing, whatever the tenant is running there. So all of these are kind of common threads, and there are multiple devices that are compliant with some of these common threads. And within Intel itself, there are multiple members of the IPU families. Some of them are ASIC-based, some of them are FPGA-based, and today I'll talk about some of those. So the Big Spring Canyon is an FPGA-based Intel IPU. It uses the Stratix 10 FPGAs, and it also has a full-fledged Hewitt-Lake D Xeon class processor. It's a 50 gig network processing card, which can be configured as a single port of 50 gig or two ports of 25 gig. And it has some of the standard hardware blocks that goes into an FPGA, such as PCIe, memory controller, etc. But it also has a fully compliant virtio-net and virtio-blk interface implemented in hardware, as well as some of the packet processing block. And we'll talk more about the Big Spring Canyon later. Today, I think there have already been two presentations by my colleague, Mr. Yadong Lee, on the topic of this ASIC-based IPU that we call Mount Evans. And I think some of you in the audience probably already know quite a bit of Mount Evans. Mount Evans started its journey as a custom-made IPU for Google, and right now we are in the process of providing additional software and SDK to get it in the hands of many other customers in the cloud space. If you look at Mount Evans, in a very, very similar to what I just said, you have a section that has purpose-built hardware engines for accelerating RDMA, NVMe. There is a fully P4 compliant packet processing engine that you see there. It also has inline encryption capability at full Thanks. Can you hear me? Yeah. So it has these purpose-built hardware blocks. I was just talking about the P4 compliant packet processing engine. In addition, it has an inline encryption module capable of encrypting traffic at full line rate of 200 gig. In addition, it has 16 ARM Neoverse N1 cores for additional programmability. Anything from the customer control plane to even running full protocols that are not hardware accelerated. In addition, there is also a vector acceleration block, which is a look-aside compression and encryption engine. And to harness the capabilities of these different types of IPU devices, we came up with this infrastructure programmer development kit, or IPDK. I talked about an FPGA-based IPU, and I also talked about an ASIC-based IPU. And my team, unfortunately, has to provide software for both. And as we were looking at how much of this software is really common, we realized that hardware abstraction is really, really necessary. But we also took the bold step of setting as a goal that it can run not just on Intel IPUs, but non-Intel IPUs as well. That was the goal. So it's community driven, it's target agnostic. Everything that we do under IPDK always starts its journey as a pure software target that can run on any processor, and then we, based on interest, we port it on the different hardware targets. And that can be an IPU, that can be a non-Intel DPU, or it can be a switch like the Intel Barefoot Tofino switch, etc. We did our first major release of IPDK in the month of July. It's our IPDK 22.07 release, and we are already working towards our next release, which is the IPDK 23.1, to be made in January of 2023. So a little bit about this IPDK storage use case running on IPU. So the IPDK supports multiple storage protocols. In particular, if you're talking about the host-facing protocols, then there is a support for using either virtio-blk or NVMe as the host-facing protocol. And these are hardware accelerated in some of the IPUs that I mentioned before. Once the host connects to the IPU using one of these host-facing protocols, then to connect to the remote storage, the IPU mostly uses NVMe-over-TCP as of now, but it can also be NVMe over RDMA, essentially NVMe over Fabric, as well as iSCSI. This particular design is both hardware agnostic and vendor agnostic, and different aspects of this design can be accelerated by dedicated hardware. For instance, the RDMA engine that I mentioned, it pretty much offloads most of the RDMA storage stack. The crypto compression blocks can offload the crypto part of it. And so similarly, by using other hardware blocks, we get more performance out of this. I am going to talk about the development environment here, but just something as an FYI, whatever you can get from IPDK.io website, as well as whatever we are still building, a lot of it is container based. You download containers, build on your system, etc. And there are several reasons for that. I mean, many of you have tried building open source software. You know that it's not always just the task of finding the right version of the software that you want to run, but also all the other components that this particular software needs to run, and finding the right version, and resolving all the dependencies. So we feel that shipping our solutions as containers helps the developers that way. You can think of them as integrated software stacks that are very easily deployable as well as easily testable. This is the platform. This is how the platform looks like when we prototype this storage virtualization on an IPDK software target. So if you remember the whole flow being that there is a storage application represented by this user here. The storage application connects to the IPU host, and that storage application host is, the physical host is represented here within the platform one's box as the QEMU instance. In an actual hardware environment, there would be a physical host in which there is a slotted IPU card. That is represented here, that physical host is represented here using that QEMU instance. That QEMU instance, or the representation of the physical host, is going to use virtio-blk, vhost virtio-blk interface to talk to the second container, which is the IPU storage container. This is, you can say that this is an IPU simulator. It's a software implementation of the IPU's processing. And then that IPU storage container software then uses NVMe-oTCP to talk to the platform 2, in which there is a storage target container, and that represents the remote storage pool. And this is how the whole system works. For configurability, the IPU can be configured using the SPDK SMA standing for Storage Management Agent gRPC. The physical host can be configured using the some host level host target gRPC. And for configuring the storage target itself, we have the SPDK JSON gRPC. And when we move to the actual hardware, all the interfaces remain exactly the same. So there is no new software except that the IPU storage container, which is a IPU simulator, that gets replaced by a physical IPU, and instead of the host target container, you have an actual physical host. I think this is a little bit of a repeat, but these are the roles and responsibilities of the three containers. The host target container, what it does is it runs traffic, such as FIO payload, over the exposed virtio-blk devices that exist within the host. And the IPU storage container, what it does, it runs SPDK SMA, which connects to storage target NVMe-oTCP device. And on the host side, it exposes virtio-blk interface to the host. The storage target container is responsible for creating RAM drive BDEBs and exposes them over NVMe-oTCP. By the way, you do not necessarily need to have two machines. You can actually put all of these things within one machine using the Docker Compose. We use Docker Compose to get all the containers on a single machine. And here, along with the containers that I already introduced, you have another container called test driver. Test driver actually configures the different test scenarios, runs result, exports them, etc. So now let's come back and see how this environment is going to look like when this same storage use case is run on the big Spring Canyon IPU. And the big Spring Canyon, that static 10-based FPGA containing all the FPGA IPs and Hewitt-Lake SoC. Here we are using that as our IPU. Among the three containers that I talked about before, the host target and storage target containers, these are completely hardware dependent. When we move the platform to a hardware platform, those two containers don't need to change. It is only the IPU storage container that is hardware specific. And this time you see that it is actually running on the Hewitt-Lake SoC that is part of this big Spring Canyon IPU. Many of the FPGAs contain embedded processors, but that comes at the cost of reducing the design space within the FPGAs. So in this case, we are not running anything on the FPGA embedded processor. We are keeping as much of design space available for hardware blocks, and we are running everything on the Hewitt-Lake processor. A little bit of hardware overview of the big Spring Canyon IPU, and mainly IP-centric view. See, it has, of course, standard PCIe interface, memory interfaces, etc. But it also has fully compliant hardware implementation of virtio-blk and virtio-net with live migration capabilities. And that live migration is not just from one hardware device to another hardware device. It can also do live migration from a real virtio hardware to virtio running in software. So that's a pretty powerful IP. So on the host-facing side of it, what we expose is 16 virtio-blk physical functions. And each of these virtio-blk PF has up to 8 vert queues, and these vert queues also have capabilities of rate limiting and traffic shaping controllable through APIs. And on the SoC facing side, what you have is there is one management PF for configuring the IPU. All of your diagnostic and debug tools can make use of this to get to the hardware bits of the IPU. There is a virtio-net physical function for storage packet processing, and there are 2 virtio-net PFs for this 2 by 25 gig interface to connect to external server. There is also a block that is shown here in the middle called PPBB, or packet processor block. It has several miscellaneous responsibilities for mapping host and SoC and line interfaces, but this particular hardware design also uses in-band communication through Intel proprietary header or meta tag. So this block is also responsible for adding those proprietary header or meta tag into the packets, and when needed to remove them from the packet. And a lot of configuration information is communicated through this proprietary tag. This is the Big Spring Canyon software overview. So the entity in the middle, this virtio-blk net pooler, it's essentially a channel between the host initiator on one side and the remote storage on the other side. The SMA gRPC interface is there for orchestrating SPDK application. And then there is a low-level API library that is simply called LLD IPU API library that is for configuring virtio-blk, virtio-net interfaces of the IPU. It also has hot plug capabilities. I mean, you can make a disk appear or disappear on demand. It's not just at the time of power on, you can do it dynamically during the runtime also. And this LLD IPU API is also enable that hot plug add remove kind of capabilities. These are some of the examples of the software APIs, examples for creating remote disk, examples for storage container for configuring IPU and to start storage backend application. There are facilities such as add port, set port, create device, delete device. There is new terminology not explained here, sorry about that miss, called ACP, which stands for Smart Endpoint, and the add ACP and remove ACP is for the hot plug add remove. And these APIs are all available from IPDK.io, and you can go and try out some of these. For next steps, I said that for the purpose of this particular use case, we used virtio-blk as the host-facing protocol. We are also going to enable NVMe. We are going to see if we can support multiple IPUs in the same platform and whether there are any API consequences associated with that. We have work is currently going on to do data at rest encryption on the host. We are working on a Kubernetes CSI plugin. We're also working on a common management interface for all of these virtual devices, both the virtual ports and virtual disks, and that common management interface will be based on OpenConfig, and also demonstrating virtualization use cases and live migration of virtual machines. My engineering team in India and Poland contributed to this particular demo and presentation, and you see them referred here. Vasav Raja, Artek, Philip, and Anbu. And then you can check the IPDK storage solution on GitHub. These are the links. You can also sign up for our Slack channel to get more information. And that's all I have. Questions?
On one of your first slides, you had a bullet for next generation reliable transport, but I didn't catch any discussion. That was under the Mount Evans IPU slide showing the capability. Can you speak a little bit to what you're thinking about next generation reliable transport?
So reliable transport is essentially an alternative to using TCP. So there are two main flavors: iWarp that runs on TCP and Rocky that runs on UDP. But then you have to build additional reliability layer using, DCB or some other thing. The reliable transport protocol is essentially an alternative where you can keep most of the upper level, but replace the lower layer with a reliable transport layer. this work was originally done at Google, so we are sometime probably a little bit sensitive or careful to talk about this. But going forward, we have a joint ownership of this, and this will become a standard part of IPUs coming in future.
So the SPDK and IPDK, they're like one within another, or like how are they related?
IPDK builds on a lot of standard tools, DPDK being one of them, SPDK being one of them, and all these P4 compilers, libraries, P4 runtime, etc. Those are also. So we think of IPDK as kind of a level above these things. Any other question? Thanks for joining me in this session. It was a pleasure talking to you.